Hello friends, I am Sanskriti Vag and here we are going to discuss the linear block codes. So the first question arises, why? Why we are learning this topic? So our motive to learn this topic to achieve error-free digital communication in presence of distortion and noise. So here we are going to discuss about the FEC codes, which means the forward error correcting codes. The FSC codes are mainly classified into two groups, which are block codes. The second one is convolution codes. Here we are going to discuss mainly about block codes. In block codes, every block of k data bits is encoded into a longer code word of n digits. That is, n is greater than equal to k. Every unique sequence of k data bytes is converted into a unique code word of n digits. So here are basic terms which we have to go through. So the first one is denotation. The any code is denoted by n, k format. Code word, it is the unit of bits that can be decoded independently. The next term is code length, which is the total number of bits in a code word. If a binary code has length of n, then total number of codes formed are 2 to the power n. So now let's move to our topic, linear block coding. Let us assume code word of n digits, which can be represented by C1, C2 up to Cn digits, and the code word of k digits, which are represented by D1, D2 up to Dk, such that k is less than n, which is mentioned here. Then the linear block codes will be given by C1 is equal to D1 up to Ck is equal to Dk, and after that Ck plus 1 will be H11 D1 XORing with H12 D2 up to H1k Dk. That is the remaining m is equal to n minus k terms are the parity check digits formed by the linear combination of data digits from D1 D2 up to Dk. So from C1 to Ck, these bytes are called as systematic codes. In which the leading k digits of a code word are the data digits, as it is C1 is equal to D1 up to Ck is equal to Dk, and the remaining Ck plus 1 till Cn bytes are called as parity check digits. Which are formed by the linear combination of data digits from D1 to Dk. Now let us see a formula which is C is equal to Dg, where C represents the code word, D represents the data words or data digits, and G is the generator matrix. Which has dimensions of k cross n. Now the next term is weight. The weight of the code C is the number of ones in that code word. And the next term is Hamming distance, which is given by D Ca, Cb is equal to weight of Ca XOR with Cb. Now, as our topic is linear block coding, the condition for linear codes is given by D mean is equal to mean weight. As a signal is to be error free, we have to first detect the error in the code, and then we have to correct it. For that, the minimum distance between t error detecting code should be d mean is less than equal to n plus 1, and the minimum distance between t error correcting code is given by d mean is greater than equal to 2t plus 1. As we know, the circuit that the transmitting signal is encoded first, then it passes through channel, then it is decoded, and after that we receive the signal. Which may contain some errors, which is represented by E. Let received word be represented by R vector, transmitted vector be T vector, and the error vector is E vector. So as it is not as received signal is not same as that of the transmitted vector, some of errors occur which are given by syndrome error and which is given by R dot HT transpose, where H is the parity matrix. So we have to transpose this matrix first and then we will obtain the syndrome error. What is the syndrome? It identifies the bit in error. As we discuss here, C is equal to DG, that is code word equal to data digits into generator matrix. G is comprises of IK and P, where I is the identity matrix and P is the parity matrix. So after getting multiplied by D into this IK and P, we get C is equal to D into DP, and the new term is arrived here, that is CP is equal to DP, and that CP is equal to checksum bits or the parity bits. Now to find the transmitted signal from the received signal and the error, we have the equation transmitted signal is equal to R XOR with E. As we are using XOR operation here, let us discuss XOR truth table for XOR table. So when the inputs are A and B and output is Y, when the inputs both are 0, output will be Y. When one input is 0 and another is 1, the output will be 1. And when the both inputs are 1, the output will be 0. Let us discuss one example so that concepts will get clear. So for that, we have an example. For a 6,3 code, the generator matrix G is given by this, and we have to find all corresponding code vectors, minimum Hamming distance, that is D mean, error detection and error correction capability, parity check matrix, that is H, and we have to find the error if received code is given here. So let us solve it. As here the denotation is given by 6,3, we get as n is equal to 6 and k is equal to 3, therefore m is equal to n minus k is equal to 3. Therefore number of combinations formed or codes formed is equal to 2 की power m is equal to 2 की power 3 is equal to 8. And here we have given the generator matrix. So we know that generator matrix comprises of identity matrix and parity matrix. Parity matrix is of dimensions k cross n, and identity matrix is of k dimension. From here we get that k is equal to 3, and we get from here identity matrix is equal to 1 0 0 0 1 0 0 0 1, and the parity matrix we get as 1 0 1 0 1 1 1 1 0. So as we know that 8 combinations will occur, so let's write it in this table: 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. As we know that Cp is equal to dP, occur, we have D and P matrix. So we will get CP1, CP2, CP3 is equal to D1, D2, D3 into parity matrix, which we had find out here 1 0 1 0 1 1 1 1 0. From here we get CP1 is equal to D1 XOR D3, CP2 is equal to D2 XOR D3, and CP3 is equal to D1 XOR D2. So from here we can find out the values of codes from C1 to C8. Therefore CP1 is equal to D1 XOR D3. So we know that the table of XOR, so 0 XOR 0 is 0, 0 XOR 1 is 1, 0 XOR 0 is 0, 0 XOR 1 is 1, 1 XOR 0 is 1, 1 XOR 1 is 0, 1 XOR 0 is 1, and 1 XOR 1 is 0. Similarly, CP2 is D2 XOR D3. Therefore 0 XOR 0 is 0, 0 XOR 1 is 1, 1 XOR 0 is 1, 1 XOR 1 is 0, 0 XOR 0 is 0, 0 XOR 1 is 1, 1 XOR 0 is 1, 1 XOR 1 is 0, and the third one is CP3, that is obtained by D1 XOR D2. Therefore 0 XOR 0 is 0, 0 XOR 0 is 0, 0 XOR 1 is 1, 0 XOR 1 is 1, 1 XOR 0 is 1, 1 XOR 0 is 1, 1 XOR 1 is 0, and 1 XOR 1 is 0. So here we completed our first part, that we had find all the corresponding code vectors. Now the second part is minimum Hamming distance. So we discussed that Hamming distance is given by the weight of CA XOR CB. So we have to find weight of these codes first. So weight is given by the number of ones in that code word. So here number of ones is 0, number of ones is 3, number of ones is 3, number of ones in C4 is 4, number of ones in C5 is 3, number of ones in C6 is 4, number of ones in C7 is 4, and number of ones in C8 is 4. Therefore, as the Hamming distance is given by D mean is equal to minimum weight, here it is of 3. Therefore, we get D mean is equal to 3. That is equal to Hamming distance. Now the third is error detection and error correction probability. So we had discussed here that the error detecting code condition is given by D mean should be greater than equal to T plus 1, where T are the number of errors. Therefore here D mean is equal to 3. Therefore 3 is greater than equal to T plus 1. This implies that T is less than equal to 2. So from here we get that it can detect up to 2-bit error. And now after error detection we have to correct that error, and the condition for that is D mean should be greater than equal to 2t plus 1. Therefore 3 is greater than equal to 2t plus 1. This implies that t is less than equal to 1, which implies that it can correct 1 bit of error. Now the fourth part is we have to find the parity check matrix, which is represented by H. Now the parity check matrix is consist of PT transpose and IM. We had find the parity matrix here, so the transpose will be taken as by interchanging the rows and the columns. So we get PT as 1 0 1 0 1 1 and 1 1 0, and the value of M which we had find here is 3. Therefore identity matrix is of order 3. Therefore from that we get H is equal to 1 0 1 1 0 0 0 1 1 0 1 0 1 1 0 0 0 1. and to find the parity check, and here we find the parity check matrix. Now the last part is that we have to find the error if received code is this much. So here R is given by 100011. As we know, the syndrome is given by R dot HT, that means H transpose. We will solve it by transposing the parity check matrix from here 1 0 1 1 0 0 0 1 1 0 1 0 1 1 0 0 0 1. From here we get that 1 XOR 1 is 1 multiply 1 1 0 0 0 1 1. Multiplication of row with the column 0 0 0 0 1, and with the third is multiplication is 1 0 0 0 0 XOR 1. So we get as syndrome error as 1 1 0, since 1 XOR 1 is 0. So we find the syndrome error. Now to get the error in the received signal, we have to see the position of the syndrome in this HT matrix. So at the index of 3, we are receiving that error, that is here n is equal to 1, here it is 2, and at n is equal to 3, we are receiving the syndrome error. Therefore, error is occurring at third bit. Therefore, it will be given as 0 0 1 0 0 0. Now, as we know that the transmitted signal is given by T is equal to E XOR R. We will perform the XOR operation between E and R. We have E as 0 0 1 0 0 0 XOR with R, which is given as 1 0 0 0 1 1. So by performing XOR operation 0 1 1 0 0 0 1 0 1 0 0 0 0 1 1 0 1 1, this is the transmitted signal which we had passed earlier. This is how we had find the error when the received code is this much. And this ends to our topic. Thank you.